All right, perfect. Welcome everyone to today's Radiation Belt in Space Physics seminar series. Today we're going to be focusing on particle radiation impacts, and we have two speakers, Esa Turunen and Hilde Ness. Our first speaker will be Esa Turunen. Esa is a retired professor and is currently an emeritus professor at the University of Oulu in Finland. He was responsible for their ionospheric research and measurements at SGO, coordinating the ISCAT radar and rocket measurement campaigns, and participating in several EU projects, including mobility schemes and EU cost actions. He was previously the PI of Finland's participation in the ISCAT 3D project, and we are happy to have him today to discuss forcing of the lower thermosphere middle atmosphere by high energy electron precipitation in a 1D coupled neutral and ion chemistry model. Esa, if you would like to start.
Okay, thank you very much. Thank you for this invitation. I'm happy to be speaking again after this long pandemic time and breaks, which we had to suffer all. And if I start sharing my screen. Allow Zoom to show your screen. How do we do that?
You may need to set up some permissions.
Yeah, I need to set up a permission, sorry.
Well, this way we did get to 30 as anticipated.
Zoom can't store unless it's stopped.
You may have to reconnect.
In that case.
Are you sure you have sharing enabled, Sasha?
Yes.
Okay.
It's about permissions to share the content. If you haven't done it
on the live
Mac,
stream,
you need to just set it up. Oh, excellent.
We are somehow online.
Yes.
And if I just say here,
play.
Do you see my screen?
Yes, everything is great.
Is it moving?
Yes.
I mean, do you see
yes.
You see a moving out in the background?
Absolutely.
Okay. Do you see my cursor on if I'm pointing something?
Yes.
Even better. All right, so I wanted to speak now for a short 20 minutes about forcing of the lower thermosphere middle atmosphere and by high energy electron precipitation. But of course, time is short to speak about all the electrons, so I'll just concentrate on some examples and show how we are using these tools where we try to understand what is happening. And then I hope that Hilde and Tyssøy will actually wrap up the impact part of all these processes in her talk later. So, of course, I want to make some introduction first with some slides. And first of all, we today call our field of study as geospace environment. And we do know this is a highly dynamical region with couplings of very large regions and very small regions between each other, interactions where you might study one interaction with some specific measurement, but actually you can't really understand the whole entity unless we have a lot of measurements. So some slides here just to illustrate the situation that, for example, magnetosphere in itself, and of course radiation belts in the magnetosphere are one example of areas where geospace environment is currently being investigated. But then if you go to ionosphere and atmosphere, to a smaller part, all the time we find interactions which reveal more and more tiny details, and this whole looks like a mess which we need to somehow understand as a whole. And if I just now take an example on how research is being done here in Finland, here's an example of selected topics for research in near Earth space environment in a grant proposal by my university, by Professor Anita Aikio. And there we, of course, selected one of the main questions, which is kind of a topic of this seminar too. Let me try to find my cursor. It's now so that I can't really control anything I see. All right, so I'm missing part of my whole screen, but you see the question. So what is the effect of these high energy particles on atmospheric ozone, which is an important gas determining the processes and the balance of many important aspects. And actually, can we imagine that space processes could affect temperature via complicated chains like the one we are having here today? But I would like to point out some philosophy here. How do we define understanding in general? We would like to understand what is the impact of particles in our atmosphere. We normally use models for understanding. We have three basic types of models: statistical types, assimilation types, and physical principles models. So I want to speak about the physical principles model we are using today. But all these models, which I now quote as understanding, they always need data. Statistical models need empirical data. Assimilation models like weather models need data as drivers. And the physical principle models, they need key input data, both for their construction and for the verification. So if I take this question about force in the atmosphere from above by the high energy particles, here's an example of all-sky image of pulsating aurora. And I'm asking, do the pulsating aurora destroy mesospheric ozone? And is there any effect below the altitude of this emission where the emission of the pulsating aurora occurs? So then, of course, I need to have a model of these things. And then I'm asking, how good is my model? And of course, I need to get the reasonable consistency with comparison of model to experiment. That's the first point. And of course, we should, in the end, be able to make successful forecasts of the future with the model. All right. So here's an image. I hope you can see the colors. There's a green background emission of aurora covering the whole sky. You see the stars, Ursa Major there, the Big Dipper. And then there's blue emission. And we know that the blue emission comes from ionized nitrogen molecules. And in this case, we anticipate that this is not a scientific camera, it's just a normal system camera. But we anticipate that high energy electrons are present in our view here. And we know that 1 mega electron scale would penetrate as low to as to upper stratosphere, like 50-60 kilometers altitudes. And of course, we know that we expect, due to this increased energy deposition in the atmosphere, changes in dynamics, increased ionization, conductivity changes, radio wave propagation effects, and chemical effects. And we get increased dissociation, chemical effects due to that, and increased excitations, again, changes some chemical rates, and of course, like in this view, just beautiful aurora borealis. And now we would need to somehow incorporate all this into our model, which makes our understanding. So here's an example. This is a schematic figure from Miyoshi et al. Recently in scientific reports about aurora somewhere on Earth. And pulsating aurora is, of course, emission, which is having some repeated patterns with some frequencies due to precipitating particles, which originate somehow in a rhythmic manner in certain timescales. And here we know that relativistic electrons would be seen to precipitate at the southern areas from the standard auroral zone. So one question would be what happens in the atmosphere with these relativistic electrons, for example. So I'm showing one example of this. And this is an old figure of mine showing you how the penetration of different energies of particles reaches the atmospheric altitudes as shown as ionization rates. And the right panel shows you electron ionization rates. You see how 1 mega electron volt energy reaches just at the 60 kilometers altitude and like upper stratosphere. So when we go to relativistic energies, we would reach those altitudes. So just for summary of these effects, auroral electrons normally are really like 10 kilo electron volts, below 30 kilo electron volts. So the emission would be seen in the atmosphere above, let's say, 90 kilometers and above. Medium energy electrons from 30 to 300 kilo electron volt, they are more energetic, below 100 kilometers always, down to something like 80, 75, 70 kilometers. And then we have the high energy part, which we know that is present in radiation belt electrons, like more than 300 kilo electron volts. And then we are asking, how frequent are those events in atmospheric, if you think about the loss of these electrons from radiation belts? How frequent is the atmospheric loss? Which kind of areas does it cover? Just some schematic introductory pictures here. The left panel shows the variability of ionization rates by various ionization, mainly particle precipitation agents. But it's important here in this figure to compare this pale brown, which is the solar EU. If you see my cursor, I can't see my cursor. I can't show really you now at the moment. I don't know how to show. This pale brown area, solar EUV and X-rays, that's not so variable. And the variability here is caused by the higher energy part of the radiation. This is interesting. If you compare that to the variability of all these particle agents, like auroral electrons above 100 kilometers normally, or radiation belt electrons from upper stratosphere up to 100 kilometers, or in some cases, these solar protons, which even penetrate to normal stratospheric altitudes. And then you see the galactic cosmic ray background, which is variable, of course, due to the conditions in the interplanetary space. Also, that is not too much variable compared to the particle inputs. So this is an interesting topic. I'll not speak about the processes shown on the right panel. I just mention here that the ionization degree at these altitudes in lower thermosphere and middle atmospheric altitude is very, very low. It's like 1 part of a million. But nevertheless, still this high energy, ionization by high energy particles plays a role in chemistry. And this, I think, is very, very interesting. So here's some simple statement that when we have this middle atmosphere as a coupling region between space weather, ionosphere, lower atmosphere, we really would like to know how do all these couplings happen. And I'll just show now an example of our work where we have concentrated on how ion chemistry actually couples to nuclear chemistry, even with this very low ionization degree. But then you saw already that the particle inputs cause high variability in the ionization rates. And what is now the relevance of all this is, of course, that when we want to understand our climate, when we want to have a model for the future for the next 50 years, and we want to make better climate assessments, we need to understand all these coupling processes, including the variability of the forcing by particles. And catalytic ozone destruction is the interesting chemical process, which is also then in substantial amounts affected by particles. So here's a figure by Craig Roger, showing you some, on the left panel, showing you some particles with their energies penetrating to some altitudes. And then we do have neutral compounds, odd hydrogen, odd nitrogen, generated by various processes. And these appear to act as a catalytic agent, so that, for example, if sunlight is absent, we have long-lived odd nitrogen species, which may be even transported to other regions, other altitudes, other latitudes for longer-term effects. And then we may ask if this plays a role in whatever climate assessment. It's now happening. Why is this freezing? Can you hear me now?
Yes, we can hear you, but the slides do not progress forward.
Yeah, slides don't progress. Let me. Yes. Interesting. If I press escape, just take the next slide from here. So here's the schematics by Annika Seppälä on this, that we increase the ionization, we change the chemistry.
You stop sharing, Isa, without don't
Yes.
see slide.
Sorry, I need to share first.
That's all good.
Yes. So then via these chemistry changes where ion chemistry is coupled to neutral chemistry, you could then anticipate this plays a role. So how do we then want to know or calculate this? Of course, if you go back in time, like some 30, 40 years, that's a kind of time scale when we have studied this process of atmospheric impacts by particles. I think that this ion chemistry at lower ionosphere was really neglected as any significant player, just simply because of the very low degree of ionization. So people concentrated on the neutral chemistry, of course, in atmospheric chemistry. But really now this, if you think about this odd nitrogen and its normal lifetime, like one day, in the absence of sunlight, it's weeks and months. And of course, the absence of sunlight is not occurring that free. It's not always there, but it's on either hemisphere at the polar regions for several weeks, several months, depending on your altitude where you are investigating a system. The odd hydrogen is as interesting because if you have some long-lasting high-energy precipitation event, of course, you create odd hydrogen all the time when you have this ionizing agent present. And then that changes the neutral chemistry balance also via ion chemistry. The main process, of course, actually is dissociation, which we change by the particle precipitation, and that changes the chemical balance. But interestingly, then also the ion chemistry changes the balance of some chemical, how do we call this? These minor constituents. Okay, so in the end, we destroy odd oxygen and importantly ozone, which is a good absorber and emitter of infrared radiation, one of those gases which defines the atmospheric temperature. And now this figure I find always very motivating. It's a collection by Friedrich and Torkar of rocket measured profiles of electron density in lower ionosphere. And now if I'm plotting here examples by Miersch et al. From ASCAT inconsistent radar observations of these electron density profiles, you see during pulsating aurora, the green dots are kind of a background. And then during the pulsation, when the precipitation sets in during pulsating patches, you see orders of magnitude changes. And this high variability is now illustrated by this figure. Of course, these rocket profiles are not too many here. And what is then the current status? This is a bit outdated slide I made a couple of years ago, but you see here some examples that we have really verified today that there are atmospheric composition variation due to energy particle precipitations, and there are even some evidences on particle-induced regional climate variations. We could discuss what's the significance of those, but there are now several reviews even available, and I would like to advertise this recent book by James and Usanova as editors. There's a collection of very nice works. But you see here, after the blue line, which is the onset of a geomagnetic storm, changes in ozone concentration up to several tens of %, which is a kind of descending fact when the lower panel shows you how odd nitrogen has been observed to increase during this geomagnetic storm, just as an example on how these things develop. And what we did here at Sodankylä and University of Oulu, we wanted to make a better understanding of our radar measurements. So we started making a model of ionosphere in the lower part. And we first made a model just merely ion chemistry. My supervisor said to me that you don't need to care about the neutrals because it's like a sink. They are such more numerous in concentrations that don't pay any attention to neutrals. You just use them in your reactions. But then very soon we noticed that no, this is not the truth. And we need to couple the positive ion chemistry with neutral chemistry and the negative ion chemistry with neutral chemistry. And when we have three-party collisions, the negative ion chemistry, when atmospheric density gets higher and higher at low altitudes, the negative ion chemistry starts to play a role also in high ionization events. Now, this scheme you see here is not at all complete. It's not complex. It's very simple, in fact. You just write it down and then you solve all these equations. Now, time is not enough for me to show how we solve this, but this is a very simple process. So we just have a set of weakly nonlinear equations to solve. The problem here is that we have quite many unknown coefficients, which we need to estimate somehow. So we can only take, okay, upper limit or average, or okay, something is measured in laboratory and something is guessed, something is just calculated by a model. But in the end, the only knowledge which kind of certifies our model is compare with the experiments. And this, of course, is something we have done in the history. So now I saw an example of pulsating aurora seen by a satellite. You see here a photometer recording of pulsating aurora in the center, the pale blue, and that shows you variations in the emission which is detected. And now we have an ASCAT inconsistent radar measurement during that event where the footprint of the satellite was kind of close enough so that we could try a comparison. And you see how the background, the black line on the left panel is much lower than during the pulsation, the high ionization shown by the red curve. And then the question is, what kind of electron spectrum are we having, which is then driving this, or which these electrons have? The problem comes now here that the ASCAT inconsistent radar cannot measure accurately at lower altitudes. But if you use this chemistry model, we can fairly well simulate what the ASCAT is observing. And then you have uncertainty in the high energy tail of the energy distribution of your electrons. But when you input that to the model, and here's a model result, so that the uppermost panel shows you 5 consecutive days. And early in the morning at 4 o'clock, you set in 30 minutes or 2 hours pulsating aurora, which you see in the electron density clearly on the 17th of November. And then every day you see sunrise, which are those parabola, sunrise EUV generating ionization. But what happens is the nitric oxide just simply jumps out due to this activity of pulsating aura and doesn't decay. It decays slowly, slowly, slowly. Of course, HOX is more depending on direct driving, so that doesn't stay very long disturbed. In the end, you can calculate that the ozone and odd oxygen change is in the order of tens of percents. But of course, you see here that there's some uncertainty because we don't know exactly the lower altitudes, electron density at lower altitudes, or the high energy part of the precipitation. Okay, that was an example of some model calculation only, but then the question comes, what kind of spatial region, what kind of temporal duration we have for the ionizing agent, the pulsating aurora, and this is highly variable. There are some recent studies which I don't show now, which have tried to estimate what kind of scale is available here, but the conclusion here would be that we do have in mesospheric ozone tens of percent changes, which are highly variable. And then, of course, maybe Hilde will speak more about this, that the dynamics is also highly variable from year to year and day to day. So what is then the significance of all this forcing is more difficult to say. Okay, now I wanted to show an example of a model event, observed event, again with ASCAT. You see on the left the pile of color panels. The second panel from above shows you ASCAT measured electron densities, and to the lower end of the window you see that the lower altitudes down to 65 kilometers are ionized by electrons in a regular manner. And then you make a similar estimate as shown before. You see how in this case, so this is now not measured ozone variation, but modeled ozone variation based on the measured electron density. You see this 10% change here, which is, well, not too much, but then the question again comes that, okay, this is now a single event. What about other events? What about more stronger events and frequently occurring events? Okay, I skip, now my time is running out. I skip this. Of course, we can study with such a model things like Bremsstrahlung effect, which is the effect of X-rays emitted once you stop your particles by the ever-increasing density of the atmosphere when you come from above to below. And here you can simply see if you have very high fluxes and very high energies, you then only start seeing some effects by the Bremsstrahlung at low altitudes. But maybe I should soon stop. I just wanted to show you once more the tool which I've been using is the ASCAT inconstant radar, which you see there in the image. And this is going to be replaced by the ASCAT 3D radar, which is a phased array system, has 30,000 antennas, and then you generate a three-dimensional image of your ionospheric target. And the frequency of the radar is also selected so that we should get better estimates of lower altitudes down to 60, 50 kilometers in a three-dimensional volume. And the important number here in this figure, this is an animation by Greg Hansemann, is the 125,000 microseconds, which was the time which it took to make a reasonable, this is of course an estimate. So we anticipate that we are able to make measurements of pulsating aura, for example, in this region with unprecedented accuracy. And this should be available within 1 year, depending on how all the delivery of and assembly and testing of the devices go. But sometimes end of 2023, beginning of 2024, we should start having measurements by the A-scan 3D. All right, this is what I wanted to show as an example. And if you have any questions, I'm happy to try to answer. Or maybe the questions should be asked after Hilde's talk, when she speaks about the dynamics.
Sasha, do you want to do questions at the end of both? Or?
It is your call, Kyle.
Okay. If we have any questions now, we can go over those. I have a quick question. You did show a lot of electron precipitation. Has there been any work comparing the relative efficiency in the NOx and HOX for proton and electron precipitation?
Yes, this is the interesting question, because the work started by making proton precipitation, because that was, I would say, it was easier to measure the fluxes of incoming protons, which we then anticipated. And of course, we saw from measurements that these precipitated in the polar cap area, while the electrons have much more complex patterns for the spatial coverage of the precipitation. So with protons, it was really a lot of work done from the very beginning, like starting from end of 1980s. And it appeared in the end that satellite measurements, direct measurements of ozone or nitrogen really were consistent with measurements of the proton fluxes. And so this kind of made a very valuable consistency check between the models and or expectations and then the measurements. And then, of course, the question, how does this compare to what we now know about electrons? Do electrons actually play such a role? As we know that the solar proton event, when it occurs, can really make a huge difference, and even down to stratosphere. But they are not so frequent. Today we know that that electron precipitation events are much more frequent, and some of those can make, depending on the altitude, they can make similar effects. Solar proton events can make huge effects in stratosphere, or let's say detectable effects in stratosphere. The electron precipitation makes direct effects only in the mesosphere, but then indirect effects, which are highly variable. According to model estimates, there should be sometimes even comparable to some solar proton events. So now the question just comes, we need satellite data and we need model estimates from long cycles, several solar cycles, and this part we are lacking. So we don't really have accurate descriptions of the precipitating electrons and for long times and for whole planet coverage. So there have been comparisons, yes, and I didn't show the latest results by some other teams, but now it seems to me that the work we started, that we wanted also to select how the electrons make effects, it seems to have some significance. Of course, not like the normal aurora are not comparable to solar proton events in their effects, but some specific cases, yes. At some specific altitudes, yes.
Okay. So I think you briefly touched on this here, but Alison Janes has a talk, or not a talk, a question, sorry. What measurements do you think would help fix this or help address this problem?
Yes.
If you could have the perfect setup of instruments or experiments, what would that be?
Okay, so first of all, we need X-ray imaging of our atmosphere at various energies from above. So if you make the X-ray imaging from below, like from a balloon, then you are in trouble because your image gets obscured. But from above, you can really see the French trial about the particles precipitation, and that would map you the spatial coverage. Of course, the problem here again is that satellites are moving always, so it's. I would say that first of all we need this is missing. We don't have this X-ray images from above for relevant relevant energies. And then, of course, I could imagine that if the modern CubeSats would develop, that you have a fleet of your CubeSats, and then of course you would need to have specific means to monitor the neutral atmospheric composition. But that can be done optically, and of course balloon platforms are such that they can fly above clouds, and from there you could observe optically also the neutral composition of the atmosphere. But something which measures the ionizing agent more accurately in space and time, so that it's not only one orbit here and there, but it's also measuring like constantly as an image, so that you could compare that with your continuous ground-based measurement. Mm-hmm. So it's clear that the incoherent scatter radar like ASCA3D is not able to solve these questions without other measurements. But that then is very interesting that when we will have a radar like that, which is like 100 times better radar than earlier ones, and then compare the measurements with some new satellites and even fleets of satellites.
Yeah, it sounds like a potential white paper for the decadal survey coming up for anyone interested.
Yeah, and then I may want to show you something that's a commercial. Please come to Sodankylä, come to our institute. There's a Versim workshop. You'll find information on the webpage of Sodankylä Geophysical Observatory, and there's a school also. And you asked about the instruments. This is an old figure about balloon measurements of X-rays, showing that they maximize during declining phase of solar cycles. And of course, these are very important. Robin Millan and others have made interesting measurements with these barrel platforms, but these should be continued in much more frequent manner, to my mind, and various regions. So there's also something to do with the balloons, which is missing today. More, I would say, better measurements like X-ray imaging also from the balloon platforms.
Right. Excellent. Thank you, Isa. So with that, we'll move on to Hilde. Hilde, if you want to take screen, we can make sure it works. Perfect. Yep, we can see it. So Hilde is going to continue this series discussing the impact of radiation belt electrons on mesospheric dynamics. Hilde was a young Center of Advanced Study Fellow and is currently the lead of the particle precipitation group at the Birkeland Center for Space Science. Her research bridges the interdisciplinary field of space physics and atmospheric science with a focus on the effect of energetic particle precipitation on the atmospheric system. So today we're happy to have Hilde discuss the impact of radiation belt electrons on mesospheric dynamics. So Hilde, if you would like to start, you can go ahead.
Hi, thank you for the introduction, and thank Isa for a nice introduction to the chemistry part, which makes my job a bit easier. So as the title of my presentation suggests, I will be focusing on energetic electrons from the radiation belt. And the community often labels these as medium energy electrons, typically in the energy range from 30 keV till 1 MeV. These electrons will, as Esa showed, deposit their energy throughout the mesosphere and will increase the production of HOX and NOx gases. So I will try to focus a bit more on what happens after these particles have changed the chemistry and the state of the art, or the current theory, basically focus a lot of what NOx does to the atmosphere. And during winter, without fertilizers, NOx can stay on, have a lifetime of weeks and months, as Esa told us, and then can be transported to other atmospheric layers. So even if it's being produced in the lower thermosphere, the residual circulation can move it down to the stratosphere. And it's first in the stratosphere that it's starting to get really efficient in destroying ozone through these catalytic reactions. And as ozone is radiatively important, it's important for the radiative balance. It absorbs UV, it emits infrared. So changing ozone will change temperatures. And if you change temperatures, you might change gravity wave propagation or where they deposit their momentum and winds. And these feed back into each other. And the clue is that if that change is sufficient to change the strength of the polar vortex, it might link all the way down to the surface. But I want you to notice a few things in terms of this cartoon. It is that HOX is not included like as a really important parameter, and it's basically what's going on in the stratosphere that is important. But before we deal a bit more on the effects, I will ask the question, do we know how much energy is being deposited into our atmosphere, or how many electrons are hitting our atmosphere? And then I will talk a little bit about what flux level do we need to make this interaction going. Okay, so precipitating auroral and radiation belt electrons are now considered as a relevant part of the natural forcing of the climate system. So for the first time, it's been recommended as part of the input into the couple model intercomparison project, which is quite good, but still there are very few models that can include these particles. So it's a step forward, but it's not. We don't know the answer in terms of the effect, unless the model can implement this. But it motivates us to look at the ionization rates that is included, and recent studies suggest that the forcing that is being recommended currently is underestimated. And I've been co-leading a working group together with Miriam Sinhuba, which is a collective effort to address this point. What do we know about the ionization rates coming from these medium energy electrons? And what we did was to compare 8 different ionization rates that has been included in model studies. And the fun part or strange part of that is that all these ionization rates are based on the same instruments. And just by a quick look by eye, we see that these 8 ionization rates are quite different. These are log scale, so they vary by an order of difference. The same observation ends up being quite different in energy input into the models. So we need to understand the ionization rates that we're using in order to understand the uncertainty of the effect. So the ionization rates, we make choices basically. So when you calculate the ionization rate, you have to have a method for doing that. And also you have to choose your background atmosphere. So that might be different in these 8 estimates, but it's the main difference comes from how we're handling the data from the instrument. And the instrument we're using is POES-MEPID. And the reason for that is not that it's a fantastic particle detector, but it has these 2 telescopes where the 0-degree detector, as we call it, at high latitudes, it looks along the magnetic field line, so it looks within the loss cone. So some part that is separating the 8 ionization rates that we compared is whether or not they correct for low energy proton contamination, which of the energy channels is being applied, what upper limit they are setting, the choice of telescope, the choice of energy spectra, if you sort by magnetic local time or not. So there is a lot of choices that we make based on the observation that we have. And the main difference between the estimates that are available is the choice of telescope. 5 of these ionization rates are using the 0-degree detector. And at high latitudes, it looks within the loss cone, while the 90-degree detector is looking at the edge of the loss cone or outside. This is just one example of a geometry. So this will vary as the satellite, the low orbiting satellite passes over the pole. But it wouldn't matter if we had isotropic flux levels if we used the 0 and 90-degree detector. Then if we look here at the red area, if this is the particles, that the electrons that are within the loss cone, it wouldn't matter if we use the 0 and 90-degree. It's about the same level. But in particular, when we are at the end of a storm, then we often have anisotropic flux levels at these energies. So then we have the pitch angle distribution within the loss cone is getting less and less toward the middle of the loss cone. So then, if we're just using the 0-degree detector, we systematically underestimate the number of electrons that is being deposited into the atmosphere. Well, only using the 90-degree will overestimate it. So 3 of the 8 ionization rates estimates are using both of these because of their expected anisotropy. So, but we're using different methods. So, as you see here, we have a logarithmic mean of the 2 telescopes, an estimate of the pitch angle distribution as sinus function, or in my group, we're using the Fokker-Planck equation to estimate this distribution. But it kind of tells us that even if you read about a paper that's saying, oh, we're using MEPID data as input, it can be quite different input. And as I mentioned, the most extreme ionization rates differ orders of magnitude, both during geomagnetic quiet time and during geomagnetic disturbed region. And this is just one example from almost a month where we had a strong geomagnetic activity in 2010. And it's evident that these, even if we're using different method, the ones that are based on the 0 and 90-degree detector has much higher fluxes compared to those just based on the 0-degree detector. But it's impossible to say that one is wrong or one is right because it's we do not have good enough measurements. So based on the question that Isa got, then I would say that we really welcome the CubeSat initiatives in terms of being the ones that are targeting the electron precipitation into the atmosphere, pitch angle distribution. Because we see that the largest discrepancy is found when we are expecting strong anisotropy, which is at the end of a storm. Then we have the largest differences between the different estimates. In the paper where we have shown this, we also compare how the weakest and strongest ionization rates impact the HOX and NOx gases, and we also have a companion paper comparing different ionization rates into different models. to get a kind of idea of the uncertainty in terms of the energy input and its impact. But going back to what's being recommended into climate models is this. So when you see studies, it's a minimum impact that we are looking at if we're using that CVIP recommendation. So to ask the second question, like for the first question, to sum up that, is like, what are the EEP fluxes hitting our atmosphere? Well, we don't know yet. We have a kind of, as I showed here, a range. So maybe a minimum and maximum, like the uncertainty, like when we're expecting what's coming in. But an equally interesting question is, how strong does the EEP fluxes or ionization rates need to be to impact the dynamics? I'm getting some echo. I'm not sure. Is it echo or is it someone trying to speak?
No, there is somebody has a hot mic, but I cannot mute them for whatever.
Okay, yeah. As long as it's not me, then it's okay. So next question. I went a bit fast on the first part. So ESA showed a chemistry model, and we have been playing around with a chemistry climate model, which has dynamics and is in 3D. So the whole atmosphere chemistry climate model, WACCM, is one of the few really high top models that can implement these ionization rates, including both auroral electrons and medium energy electrons. It's different version of WACCM, but the standard one is going up to about 140 kilometers. Typically, when we try to look for impact on the dynamics, the model is run in a free running mode because we want the stratosphere to respond. But when we played around with it, we have nudged it to target what's going on in the mesosphere itself, kind of to question a little bit, challenge a little bit this presumption that it's NOx in the upper stratosphere that is making a change. So when we run it in a specified dynamics mode, the temperature and wind field are nudged up to about 50 kilometers. And remember that in the standard, the recommendation is to use the minimum forcing of the 8 that I showed. So we are, when I'm saying that we are playing around with it, we are just trying to see what happens when we run the model with both auroral electrons and medium energy electrons, and when we just exclude the medium energy electrons to see if there is any differences at all. We have chose the same year as that the intercomparison project, which compared the different ionization rates, and that was targeting the strongest event throughout that year, 2010. And 2010 is not the most interesting year. It's the end of the deep solar minimum that we had. So we see that the first part of the year is quite, it's not much happening until the sun starts rumbling a little bit more. So the next panels here shows the ANO in the upper mesosphere averaged over a latitude band from 60 to 70 degrees north. The blue line shows the WACCM simulation including medium energy electrons. And the green line is showing when we have excluded medium energy electrons. And as expected, when you look at this strong event, there is more production of ANO, and there will be more ANO in the medium energy, in the MEE run. And it's also here in the black line where we showing the difference more in the MEE run. That's what we expected. But then we saw something really strange, which we struggled a bit with, and that was this part. Suddenly, we see some time where we have less anode, despite that we have higher production. And we didn't really expect much dynamical change as we had nudged the stratosphere. So what can make a weaker anode volume mixing ratio when we have more production? And the answer to that, I believe, is that we have less transport from above. So something has changed the dynamics between when we include the ME compared to not including it. Looking at the wind field, this time period in the beginning of the year stands out even more. So there is something occurring in the beginning of the year at the end of January. This is a period in time where we have a stratospheric warming, and that signal is in both model projections as the model is nudged, because that signal comes from below. So in both cases, we have a sudden stratospheric warming. And as the name of that is that it's a period in time where you have higher temperatures. That polar vortex that you have throughout the winter, typically that can be slowed down, and even the wind can reverse, and then it's we call it sudden stratospheric warming. Not an expert in that part, but it's we see that clearly in the zonal wind, which is shown here over the entire. The lower edge here, this is in pressure level. So the lower edge is where the model starts running free, so above 50 kilometers. And these lines here mark the coldest temperature in both the MEE and no-MEE run. So it's where we find our mesopause. And we see that sudden stratospheric warming that was defined to occur on the 23rd of January. So we look 20 days before and 20 days after that time period. And in both runs, we see the signal of the sudden stratospheric warming in the mesosphere. And here we see that wind reversal in both runs as well. But there is some significant differences in this time period between the runs. When we included the MEE, it's almost like it's trying to stop the sudden stratospheric warming signal. It's trying to make the wind go the right way again. And it kind of changes a bit the strength and the timing of when this ends. And if we then look at, it's very clear when we look at the differences of the zonal wind between the two runs. And then we also see kind of what's happening in that with the anode throughout that period. And it seems like it's almost like this signal that's showing the difference is propagating down. So what I think we're looking at is that after a sudden stratospheric warming, that residual transport gets stronger. So we have a time shift between the two runs when you have more anode being transported. And then that's why it looks like it's less anode in one run compared to the other, because of a time shift in when this residual downward transport occurs. But the important part is that we did not expect any changes because we had nudged the stratosphere. So this means that something will happen in the mesosphere itself. And remember that we're using the weakest forcing in this case. So if we had used a stronger forcing, then maybe that change would be even stronger. And the most fun part to me is that this occurred in a time period where we had almost just like a background drizzle from the electrons. That forcing being used is scaled to the AP index, so it's very representative what we're looking at here. So there is no big events in the time period where we had the change, where it appeared to change something with the dynamics. So in terms of the question I started out with, it's like, what are the EEP fluxes hitting our atmosphere? Well, we don't know the answer. We have kind of an upper and lower limit of what we think is the energy coming in. But for the question, how strong does these fluxes need to be to change the dynamics? Well, maybe it's not one answer to that question. That flux threshold might vary alongside the dynamical preconditions. So maybe if we have a stable atmosphere, it wouldn't matter if we dumped the entire radiation belt into the atmosphere. While at other times, when the atmosphere is what we call dynamically unstable, just a weak drizzle might be important. So as typically happens when we are doing research, is that when we're trying to answer one question, we end up having a new one. So if I should make any conclusion, it will be that I would add a new question. When will energetic electron precipitation impact the atmospheric dynamics? It needs to be seen in context with what the atmosphere is doing itself. So we changed this initial figure to make a new working hypothesis, which I hope we will hope see results from not just from what we're doing here in Bergen, but also other people. So, and it's almost the same, but we have added Hawks because what would change what's going on in the mesosphere is need to be Hawks, because NOx does not become really efficient in reducing ozone until it gets down to the upper stratosphere. And we have kind of weakened the vortex a bit, so we have more gravity waves. So maybe when that is happening, we get an increased interaction, a closer connection between these feedback loops. And we also lifted that feedback loop a little bit higher up in the atmosphere. So I don't believe, based on what we see, that it's limited to the upper stratosphere itself. But we might want to look at what the mesosphere is doing as well. And it's kind of interesting also that it seemed to change how a sudden stratospheric warming was acting, because that might very well be a pathway all the way down to the polar winter surface climate, because we know that sudden stratospheric warming is really important in terms of, for me, sitting in Western Norway, a sudden stratospheric warming will mean that we get a cold winter instead of a dark, wet winter that we typically have. So that's it for me this time. New results, but I'm hoping it made sense.
Absolutely, that's an exciting update and development. Do we have comments or questions online? Robin?
Yeah, I just have a question. So Isa presented NOx as being more important, or hawks going away really fast, and so you're kind of putting hawks back onto the plot here. So just curious, what is there do we need more measurements to better understand the effect of hawks, or yeah, anyway, just curious about your comments about that difference.
Yeah, now hawks would definitely not last long. It will disappear after an event. So, but now we're contrasting like absolutely no ME. So you're kind of turning off the hawks production and all. So it's an unclear signal, I would say, when we're looking at hawks in this model run. It seems like we get an ozone reduction. I have a figure showing that. So, but it's OH here is like, it doesn't have a clear signal. But if we look at ozone difference, there is this band consistently here where we see like less ozone. But the big changes is due to the difference in the dynamics between the two. So I'm putting hawks back, but I'm not a chemist, so I cannot say that it's not a no at all. But at least I've been told is that it's it's not efficient in terms of getting the catalytic reactions destroying ozone in the mesosphere. But maybe Isa knows that better than me, knowing the chemistry a bit better. But I think based on what we see here, we cannot ignore the hawks completely. But it will not accumulate in the way that NO will.
Very interesting. More comments or questions? We're a little bit running over the time.
There's one in the chat.
Oh, is there? Is the EEP forcing balanced in the spatially uniform way in the Waccamac runs at the longitude and radiation belt latitude?
It's placed in this standard, like the default version that we're using here. It's uniform in terms of magnetic local time, but it's not like over the entire hemisphere. It has this latitude band that is prescribed by this APEP forcing. That's based on Max van der Kamp's model from 2016. So it's spatially uniform in terms of magnetic local time, but it's placed in magnetic coordinates. So what we're showing here is a geographic, the response in a geographic latitude band. I don't know if I'm answering the question.
And thank you, Grant, for a great question. More comments or questions? It's definitely overall a very exciting topic that hasn't been traditionally considered to be as a core kind of radiation belt science, but we're learning more and more of the importance of impacts from these results, including Hilde's and Isa's, of course, work that they presented today.
So I just one comment, so to just make sure what I'm showing here is preliminary results, so it's not like definite.
Aren't they all, Hilde? All our results are always preliminary and always baked. Yeah. So that's always understood. And it's very exciting. Thank you. And thanks, Isa, of course, and thank you both for staying up late and giving us fantastic talks. If there are no more comments or questions, I would like to also thank everyone who dialed in And we will do it again in 4 weeks. Please stay tuned for the announcement of the next topic. Thank you, everyone. Have a good weekend.
Thanks.